So, why is the observable universe about 46 billion light-years in radius, and the universe is only 13.8 billion years old? In the James Webb Deep Field images, some galaxies we see are currently receding from us faster than light, something you infer from how extremely their light is shifted toward longer wavelengths, meaning redder colors. Yet their photons, the particles of light, still reach the telescope. A light-year is a distance. How far light travels in 1 year, so multiplying the universe's age by that distance per year seems like it should cap what we can see. But the observable universe is defined by what light has managed to reach Earth since the hot, dense beginning called the Big Bang, and the 46 versus 13.8 mismatch is telling us that distance in cosmology is not a single fixed idea. Space is not a rigid stage. In general relativity, Einstein's theory, where gravity is curved space-time, the combined geometry of space and time, the geometry of space can stretch, so the separation between distant galaxies grows even if neither galaxy moves through its local space. Cosmologists track this with the scale factor, and we measure its growth from redshift, the shift of galaxy light to longer wavelengths as the light wave is stretched on its way to us. The farther the galaxy, the larger the effect. Imagine two ink dots on a rubber sheet. The dots do not slide, but the sheet lengthens, and only objects held together tightly by gravity, like the solar system, avoid being pulled apart. So, a photon can spend 13.8 billion years traveling, while the distance to its source grows, pushing us toward that 46 billion light-year radius. Doesn't the speed of light rule out anything receding from us faster than light? Relativity limits how fast objects move through local space, but the recession speed is different. It is how fast the proper distance, the distance you define at one moment in the universe's history, grows because space between galaxies expands. For galaxies far enough away, recession speed can exceed light speed without violating relativity, because no galaxy outruns light in its own local patch of space-time. The surprise is that we can still receive photons from a galaxy that is superluminal, meaning faster than light, receding today, because when the photons were emitted, the galaxy was much closer and the expansion rate was different, so the light gained ground before later being carried away, one more step toward 46 billion light-years. The 46 billion light-year number is a distance now, not a distance traveled. The boundary it refers to is the particle horizon, the farthest region that has had time to send any signal to us since the Big Bang, computed by combining light travel with the measured expansion history. To talk about that cleanly, cosmologists use comoving distance, which stays fixed for galaxies carried by expansion, and then convert it to today's proper distance by scaling with the current size of the universe. The clearest example is the cosmic microwave background, real radiation we map across the sky, which last scattered at recombination when the early plasma, an ionized gas, cooled enough for electrons to bind to protons and the universe became transparent. Those photons have traveled for almost 13.8 billion years, but the emitting matter was only about 40 million light-years away at the time, and is about 46 billion light-years away now. If the particle horizon is what we can see today, does the universe also have a limit to what we will ever see? In an accelerating universe, there is an event horizon, a distance beyond which light emitted now will never reach us, because the expansion keeps adding new space faster than the light can cross it. The acceleration is observationally established from type Y supernovae, stellar explosions used as standard candles because their intrinsic brightness is well calibrated, and from precision measurements of the cosmic microwave background, the effect is often labeled dark energy, meaning an unknown cause with known gravitational behavior. That means the 46 billion light-year observable radius can keep growing as more time passes, even while some galaxies we can see today will eventually fade behind the event horizon, turning the open-end paradox into a statement about changing cosmic access. The universe is not outrunning light. Our definitions were mixing travel time with present-day distance. Light from the cosmic microwave background and from distant galaxies has been traveling for at most 13.8 billion years. But while it traveled, the scale factor grew, stretching the proper distance to the emitting matter to about 46 billion light-years today. So, the galaxies that are now receding faster than light were never breaking relativity. They were closer when their photons started out, and expanding space changed the accounting. The real boundary is a horizon of information, not a wall in space, and it tells you what parts of the universe can ever become evidence. Like if this was interesting, hit the subscribe for more and turn that notification bell on.